Okay, in the last section we started the process of learning how to solve exponential equations. That's equations that have the variable and the exponent. Regular algebraic techniques you've learned up until now don't allow you methods for solving this. In the previous section we solved it by brute force, which was sort of a way of solving it without any insight. Sort of like a guessing game. You guess the value of x, you try it out and see if it's high or low. Then you improve the guess and you try to zero in on the answer in that way. Okay, so yes, it is possible to use brute force to get these values of x. However, there's a much cleaner way to do it, and that's using something called a logarithm, and it's usually abbreviated log. Okay, let's look at logarithms on your calculator. Okay, if you have a scientific calculator, it'll have an log key somewhere. Now, this calculator, which has sort of standard algebraic logic, you type in the number, then you hit the log key, and that'll show you the result. Like, for instance, if I type in 100, like right here, I hit log, it says 2. So that means the log of 100 is 2. Okay. Let's look at some logs of some of these other numbers. What's the log of 1? Hit 1 and hit the log key and it says 0. Okay, what about 10? I get 1. 1,000, it says 3. How about a number like 10 to the 9th? Okay, so if I put in 1 exp9, that's one way to get it, and then I hit log, it simply says 9. Okay, let's take a look at these and see what this log function seems to be doing. Notice that 10 to the first power is 10, 10 to the second power is 100, 10 to the third power is 1,000, 10 to the 0 power is 1, and 10 to the 9th is 10 to the 9th. Okay, so it looks like this is the power of 10 represented by this number. So it's like taking the log of a number is telling you the power of 10 that would give you this number. So put in a number, hit the log function, and get the power of 10 that would produce that number. Now, to go backward, if I'm given one of these numbers, I could simply take 10 to the y, and that would give me the corresponding value of x. You know that 10 to the 0 is 1, 10 to the 1 is 10, etc. 10 to the 9th is 10 to the 9th. So going the log x goes one direction, and then 10 to that result brings you back where you started. Now I want to point out before I go on that not all scientific calculators are the same. There's a different kind of logic on some calculators where you type in the function, like type in log, then you type in a number, then you have to say equals, and that'll give it to you. This calculator does not work that way. You simply type the number and hit the log function to get an immediate result showing up in your screen. Okay, so you'll have to get to know your own calculator. Okay, let's do a few more logs. We know what the logs of 1, 10, 100, and 1,000 are. We saw already that the log of 1 is 0. The log of 10 is 1. The log of 100 is 2. The log of 1,000 is 3. Okay? Just to recall, there's 1,000. Hit the log. Sure enough, that's 3. And so forth. It looks like we have a established pattern there. Well, what about these intermediate values? Okay? And what is it saying, actually, to say 10 to what power gives me 2? That's what it's doing for these whole number powers of 10. What about these intermediate values? Well, let's try them. Let's say I put in a 2 and hit the log key. I get 0.30103. Okay, what about 5? 0.69897. Okay, and so if you have 1, the log is 0, the log of 10 is 1, and so the log of these intermediate values, it makes sense that they're intermediate between 0 and 1. How about 20? Take 20, hit the log, I get 1.30103. Interesting. This one is just like the 2, except there's a 1 out in front. How about 50? Take 50 and hit the log. 1.69897. Okay, again, exactly like the log of 5, except instead of a 0 out in front, in fact I could put a 0 out in front of here, these have a 1 out in front. What about 200? 2.30103. How about 500? 2.69897. Okay, so all of these, 5, 50, and 500, end with the decimal part, which is 0.69897, 0.69897, 0.69897, except the whole number part out front is either 0, 1, or 2. Okay, based on that, I think you can predict what these are going to be. What about 2,000? Well, for 200, it was 2.30103. Why don't we try 3.30103? And for 5,000, well, for 500, it was 2.69897. How about 3.69897? Let's try that one. 5,000, take the log, 3.69897. Okay. Now, how do you go back? Okay. If I know a number like this, how would I find the 5,000 from it? Well, if the log goes this way, 10 to this value should give us this number over here. So if I put this in memory, and I clear it, and I say 10 raised to that value equals 5,000. Okay? The same should be true of any of these. So if I start with 200, and I take the log, I get 2.30103, just like it showed here. If I take 10 to that power, I should get back to 200. But I'm not going to do it the same way I did a minute ago. It turns out there's another key to pay attention to here. Notice that the log of x and the 10 to the y function here appear to be inverse operations. They produce opposite results. So if log of x takes you from here to here, 10 to the value takes you from here to here. Okay. And because of that, there's a special key. Notice the position of the log key, and notice what happens when I type shift. Notice that changes to a 10 to the A key right here. All right, hit shift again, you're back to the log. Okay, so let's start with 200 and take its log, and let's take that result, 10 to that power, and I get 200. Okay, so the 10 raised to the power that's shown on the screen can be gotten by taking the 10 to the A key. So we can do that with any of these. So let's try it for just 2. If I start with 2, there's its log, shift, 10 to the A key, and back to 2 again. Okay. Okay, here's a little diagram just to clarify the relationships here. If I have a starting number and I take its log, I get another number. If I take this number and take the 10 to the y function, it comes back to this original. So this followed by this brings you back where you started. Or if I start with y here, I take 10 to the, and then take the log, I'm back to where I started. Okay, so it's handy to have inverse operations. We've done it all along. When you add 2, the inverse operation is you subtract 2. When I double something, the inverse operation is you cut it in half. So taking the log of x to get y, or taking 10 to the y to get x, these are inverse operations. Now let's see how they're written here. The log of x equals y, 10 to the y equals x. Now, one of the things that I think students find difficult about studying logarithms is it doesn't look like these are inverse operations because the notation is different. It's not the Log function that's an odd notation is the exponent function that is. The log function is very standard function notation. When you say f of x equals y, you're taking the name of the function, showing what it operates on, and when you do it, you get this result. Well, that's the way logs are written. But here you have this elevated symbol up here, 10 to that power equals this. It's only familiar because you've been using this for a long time, but it's not the standard way of writing functions. Because of that, I think it's easier to see the parallelism if we, at least just informally here, think of this function written a different way. Think of this as the 10 to the function. So if I take the 10 to the function and apply it to y, I would get x. If I take the log of x, I get y. And so by simply swapping the x and the y, you can see that these two functions have the opposite effect. Take the log of x, take the result, take the 10 to that number, and you're back to x again. It's important to get used to this kind of notation because this is the way these things are used in the real world, and you have to recognize what you're working with. So if you're giving an equation that's written in terms of a logarithm, you can transform it over to an equivalent equation expressed in terms of an exponent, and so you can swap back and forth between these. These are saying the same thing. They're both expressing the relationship between x and y, but whereas this is showing the y's functional dependence on x, here's showing x's functional dependence on y. I introduced this notation basically just to clarify that inverse effect of these two operations. Before we go on, let's look at a couple of special cases here. What is 10 to the log of x? Well, if you think about this, what we're doing is we're taking x, taking its log, that's giving us this number here, and then we're raising 10 to that number. So that's like starting with x, taking its log, and then taking 10 to that number. We're right back to x again. Or if you start with a number and take 10 to that power, so starting over here, taking 10 to that power, and then take the log of the result, so take 10 to the x and then take the log of the result, we're back to x again. Up here we expressed it in terms of y, but whatever the variable, it's saying the same thing here. So 10 to the followed by log has the effect of coming right back where you started. Log followed by the 10 to the function gets you right back where you started as well. Okay, at this point I'm going to diverge from the textbook. Here is a theorem which in the text is introduced in a later section. However, this is an extremely useful theorem, and I can prove it here in basically 4 lines. And so why not prove it right now? And then we have a tool that we can use to simplify this. The author has us solving exponential functions in this section using a rather roundabout method. It's sort of like in that brute force demonstration where he showed that you can actually get answers even though you don't have all the tools available. My concern is that logarithms tend to be mysterious to people, and I would rather just demonstrate how easy these things are to work with. And so if I introduce this theorem, solving exponential equations becomes very easy. And so I'd like to do that at this stage. Okay? So let's look at this. What this is saying is if I have the log of a number raised to a power, now here I have an x up there, but it could be a to the b or whatever. Log of a to some power can be rewritten by bringing this exponent out to the front, and you can write it down like this. So the log of a to the x is x times the log of a. All right, that's the theorem. You could verify this for examples if you want. In fact, let's do that. Let's take 2 to the 3rd power, which we know is 8. All right, so if I take the log of 8, I get this number here. I'm going to put that in memory. Now let's take the 3 and bring it out to the front. 2 to the 3rd power. If I bring the 3 out in front and simply take the log of 2, here's 2, that's its log, times 3 equals, notice I have 0.9030899. Memory recall, nothing changed. It's the same thing that's in memory. Okay? So log of a to the x is the same as bringing the exponent out to the front and multiplying. Let's see how we can prove this. First of all, I'm going to make the statement that a is equal to 10 to the log of a. This is simply a restatement of what we just saw a moment ago. We start with a number, take its log, and then do the 10 to the function on that log. That's like what we had right back here. We had x, you took the log, and then you used the 10 to the function. Okay? All right, so I'm just making that statement. This is true. This is an identity. Okay? Because basically, the log and the 10 to the function are inverse operations. So if I do one, then I do the other, nothing has happened. Okay? All right, let's take this equation now and raise both sides to the x power. So I say a to the x, and over here it's this expression to the x. We know that if I took 10 to the a and raise it to the b power, this is equal to 10 to the a times b. Okay? That's all I'm going to do here. So I have 10 to this power and then raised to this power. That's equal to 10 to the x times log of a power. Okay? So I simply have rearranged the right-hand side to get my new expression here. So a to the x is equal to 10 to the x log a up here. Now, let's take the log. Now, let's look at the log of a to the x. All right? What do we mean when we say the log of a to the x? The log of a number is the power of 10 that'll produce that number. Okay? Well, what power of 10 will produce a to the x? Well, we have it right here. Notice 10 to this power gives us a to the x. So the log of a to the x is this exponent up here, because that's the power of 10 that will produce a to the x. Okay? So based on the definition of logarithms, log of a to the x is equal to x log a. Notice that this is what we wanted to prove. The log of a to the x equals x log a. And we have it. This is going to be an exceedingly useful theorem to be able to make use of. Okay, this was the exponential equation we introduced at the very beginning of this section. Let's use the theorem we've just introduced to solve this for x. Okay, so what I'm going to do is take the log of both sides. I'll take the log of 6 to the x is equal to the log of 152. Now, look at this x. I can bring that x down to the front. Okay, so I have x log 6 is equal to log of 152. And now, the log of 6 is just some number. We can punch in the 6 and hit the log key, and you'll be looking at some number in your calculator. The log of 152 is just some number. Type in 152 and hit the log, and you can get that number. And so we can treat this like an ordinary equation. Let's solve for x by dividing both sides by log 6. So x is the log of 152 over the log of 6. Okay? Let's do it. Let's take the log of 152, and hit the log, divided by the log of 6. Here's 6, hit the log, equals 2.80388. Now I'm going to put that in memory, and let's go back and show that this in fact solves our equation. So let's take 6 to this power. Remember that power is in memory, I just put it there again. So if I clear it, if I say 6 raised to the memory recall power equals, comes out 152. So we've found by using a simple application of this function and then solving it algebraically, we were able to solve for something that was in the exponent. This is something new. This is something you were not able to do in Algebra 1. Okay? Let's look at a couple more problems. This is the same thing. I could solve it the same way as what we just did, except it's actually easier if you use a little insight. Let's do this two different ways. I'm going to take the log of both sides, just like I did a moment ago. So if I take the log of 10 to the x, I'm going to just write it down. It's going to be x log 10 is equal to the log of 457. Okay? I simply took the log of both sides and I brought the x down to the front because I know I can do that. So I did that part. So that's really two steps there. But I'm introducing the fact that you don't have to do a lot of gingerbread work in between once you get fluent with this. Again, recognize the log of a number as just some other number. And so I can solve for x, dividing both sides by log 10. So I have log of 457 over log of 10, and we're home free. Okay? Let's do it. 457, hit the log key, divided by 10, hit the log key. Whoa, look at that. The log of 10 is 1. If you'd used a little bit of insight, we could have anticipated that. But I'm just going to go ahead and hit equals and finish up the problem by this method. So 2.6599. Now let's go back and look at our problem again for a second. 10 to the x is equal to this. What is the log of 457? Think of the definition of logarithms. The definition of the log of a number is the power of 10 that'll give you that number. So what is the log of 457? It is simply x. So if you think of it in those terms, I could simply write down in one step the log of 457 is equal to x. Okay, 457, take the log, I get 2.6599. Okay, so this approach is taking advantage of the fact that the 10 is the base of this exponent, and the 10 is the base of our logs. These are called base 10 logs because the log of 1 was 0, the log of 10 was 1, the log of 100 was 2, etc. We're using the powers of 10 as the basis of our log system. But if you don't pause and notice that we have a special case, it doesn't matter. If you just do it the straightforward way, like we would for any other number, we'll get the same answer. It'll just be an extra step. And here, notice we had log of 10 in the denominator, but that's just a 1. Whenever you see log of 10 or log of 100 or something like that, you ought to be able to say, aha, that's just a power of 10. I know the powers of 10 when they're whole numbers. So if this were log of 100, it would just be 2, and so forth. So if you can take advantage of that, it'll save you some keystrokes, but that's about it. Okay, here there's a little bit more involved. There's a 17 out in front. And by the way, this is supposed to be multiplication, not an x here. I can isolate this factor that has x in the exponent, and then I can take the log of both sides. Let's do that. So divide by 17, and now let's take the log of both sides. So I can say the log of this equals the log of this. Okay. Now, I can bring the exponent to the front and put it down here on the ground floor. So I can say minus 0.4x times the log of 10 is equal to the log of 29/17. Do you recognize that we have something special here? The log of 10 is simply 1. So I don't really need to write it at all. So now to solve for x, I just divide both sides by minus 0.4. So I'll take the log of 29/17 divided by minus 0.4, and that should do it for us. Okay, I'll take 29/17, that's this, take the log, and then divided by negative 0.4, 0.4, change the sign, equals minus 0.57987. 0.57987. Let's check that that works. I'll put it in memory. And let's come up here. Actually, I don't need to put it in memory. I can take that number times 0.4. So times 0.4 and change the sign equals. So that's this exponent. Now take 10 to that power. So I can hit Shift, and where the log key was, I now have a 10 to the A key. I'll do that. And then let's multiply the result by 17. Let's bring the 17 back up here. So if I say times 17, comes out 29. All right? So it all verifies. Okay, you've had a power tool put in your hands. You don't have to limit yourself to hand saws and screwdrivers and so forth. You now have at least a power drill, if not something more than that. So here's something where you can solve a whole new class of problems quite simply using logarithmic functions.